Welcome back. Today we are going through the lesson on graphing radical functions. So if you remember from talking about radical functions before, a radical function has some sort of root in it. Square root, cube root are the two we're going to focus on today, but it can be any sort of root. So in the general function, they are inverses of power functions. So reciprocal functions going on there from an exponent or a power function. And the parent function, before we do any transformations to it, is the whatever root of x. So that's our most basic function. And then we transform it. So in our transformations, we can multiply the front by an a. We can add or subtract a value inside the root with x. And we can add or subtract a number outside the root for some different transformations. So let's look at those parent functions a little bit more. Like I said, today we're going to focus on the square root and the cube root function. So for the square root function, our parent function is just the square root of x. And we remember that when we're graphing these, we don't include negative values for x because they would result in imaginary things, which is a different kind of graph. So we don't include any negatives. So I'm going to start at 0. So the square root of 0 is 0. So my first starting point is there at 0, 0. And then we find square roots where we're only finding the positive roots of them. So if I take the square root of 1, I get a positive 1 out. So I would have a point there at 1, 1. And then you can continue on. You can, based on our graph size, I'm going to kind of just go in order, but you can pick easy numbers to take square roots of, whatever works for you. So square root of 2, if I type that into my calculator, is about 1.41. So a little less than 1.5 there. And then I'm going to skip over to 4 because it's a perfect root. When I take the square root of 4, I get a 2. So when I plug in a 4, I get out a 2 here. And then it goes all the way up. So I'm going to go to 9 next, which is my next kind of easy root. Square root of 9 is 3. So I can see kind of where my function is headed. So it starts at 0, 0 and curves upward here and continues on off the graph there. Within our parent function and when we transform it, we always want to think about what the domain and range is. So remember, we are not including values of x that are negative in this because they give us imaginary answers. So the smallest non-negative number I can plug in is 0 to get out an output. And 0 is included. We took the square root of 0, so it's included. And then anything positive can happen. So we can go all the way up to infinity for our domain. Because those are the possible inputs we can put in, the smallest output I'm going to get is 0. And then we can tell from our graph and our table that the range will continue to infinity as well. So that is a square root function. Next, we are going to look at cube root functions. So for a cube root function, we can take the cube root of a negative number. It's not imaginary. So in these ones, we are going to include some negatives. So again, we can kind of think about the basics. We know that if we plug in 0, we get out a 0. So it still has that same base point there. And the cube root of 1 is still 1. So I can include that point. Cube root of negative 1 is also negative 1. So it works the other way as well. Right now, it kind of looks like a linear function. But if we try some other values, and then if I think of some other easy numbers to take the roots of, I might include something that's on my graph. So maybe 3 is going to come out to a decimal. I'll put that in my calculator. The cube root of 3 is 1.44. So if I go over to 3, go up a little bit there to about almost 1.5. And then the same thing would happen with negative 3. So it'd be negative 1.44 for the root there. So I can kind of plot those and see what's going on. So the curve that happens here is an S-shaped curve. So it looks something like that. So for this one, because we're allowed to include negative numbers, our domain is going to be every possible value. So negative infinity to positive infinity. And the range, therefore, is also going to be the same. So for cube root functions, we can plug in any number and therefore get out any number. All right, so now we're going to look at some transformations of these functions. So we're going to start with the square root function. So we remember our parent function was the square root of x, and we're going to transform that now. We're going to start with translation. So remember, translations is where the entire shape of the curve moves left, right, up, or down. Let's start with vertical shifts. So in a vertical shift, that means it's either going to shift up or down vertically. When we do that, remember our parent function, our most basic square root function, starts off something like this. So I'm going to put that on there just so we kind of have that idea of what it looks like. Now we're going to transform it. So if we shift it up 4, it means that every point is going to shift up 4. So now instead of starting at 0, 0, it's going to start up here at 0, 4. And each of those points moves up 4 spots. So our curve looks the same, but is now shifted up 4. The same thing happens if we shift down. So that is a vertical translation, down 3. When we add or subtract that number outside, in this case, we're subtracting to move it down. In this one that we did before, we were shifting it up 4. So when we translate it down 3, that means that each of those original points that we drew for the parent function now shifts down 3. So they are now down here, and our entire curve shifts. So again, a translation, this is a vertical shift, which means it's moving up if we're adding a number outside the root, down if we're subtracting a number outside the root. Then we have a horizontal shift. So horizontal meaning left or right. So same parent function here, remember? Starts the same way. Now our entire curve is going to move left or right. So if we shift to the left, remember it's opposite kind of what we would think, because inside this root is really x minus a negative 6. So that negative 6 is what's causing it to shift left 6. So that means that every point on our curve is now going to shift to the left 6. So it's now going to look like this, and we can see a little bit more of the graph where it flattens out there. We can also, for a horizontal shift to the right. So in this case, we have x minus positive 1, so that would cause it to go right 1. So shifting right 1, each of our points would cause it to move just a little bit to the right there from that parent function. So that would be a translation or horizontal shift left or right. The other two transformations that we're going to talk about here are dilations, which are stretch and a compression, vertically, and reflections, where we flip it over different axes. So again, let's start with our parent function on each graph. So it would look something like this. And then we can stretch it, which means multiplying by a number bigger than 1, or stretching it out in the vertical direction. Vertical stretch of 4, which means we can say by a factor of 4, because we're multiplying everything by 4. So those original points, 0, 0 is not going to move, because when we multiply 0 by anything, it's still 0. However, when we multiply the rest of them, you'll see that it gets taller. So this point at 1, 1, now when I plug in a 1, then I'm going to multiply the answer by 4, so it's going to shift up here. And then same thing, when I plug in a 4, I get out a 2, and 2 times 4 is going to be 8. So now this point is way up here. So you can see it starts at the same spot, but it's stretched vertically upwards. Opposite of that is if I multiply by a number that is between 0 and 1, so a fraction or decimal between 0 and 1. Now all of my original points are going to get closer to that x-axis. They're getting compressed. So let's put that parent function on there again, just so we have that as a reference. And now in this one, each of my values is being compressed by a factor of 1/2. So we're getting half as close to that vertical, or we're getting half as close to that horizontal axis. So it now looks a lot flatter. So that is a stretch and a compression with that a value out in front. The last transformation that we're going to talk about is reflections. So reflections are where it flips over an axis. in this case, with our square root function, our parent function is over here. If we're reflecting it over the x-axis, that means that we're multiplying by this negative out in front of the root. So that's a reflection across the x-axis. In other words, the y values are flipping signs. So now it's going to flip down here and kind of look like an upside down curve there. The opposite of that is to reflect across the opposite axis by putting the negative inside the root with the x. That's going to reflect it across the y-axis because all the x values are going to flip signs. So our parent function is here. And now when we reflect all those x values to the other side of the y-axis, it's now going to be facing this direction. So those are the transformations of square root functions. We've got translations left and right. We've got shifts up and down. And then we've got stretches and compressions and reflections. So we can put all those together into various functions to move that square root curve around. Okay, let's look now at transformations of a cube root function. So remember that parent function of the cube root is just the cube root of x. It's that kind of S-shaped curve that happens. We're going to transform that function now. So let's start again with translations. So we're going to shift up, down, left, and right. So again, I'm going to sketch for us just so we have the visual of it. Maybe. So we have the visual of it. I'm going to sketch that parent function for us so we know what it looks like. So it's that S-shaped curve centered at 0, 0 there. Now we are going to shift it vertically to start with. So in this case, we're going to shift it up 3. So that means every single point here is going to get shifted up 3 from where it was in the parent function. So that tells me that now my entire S-shaped curve has just shifted up. Same shape, same everything, except everything's shifted up 3. So that is a vertical translation, up 3. We also, with a negative outside that root there, we can shift it downwards with a negative. So this one is shifted down to that parent function. So everything is coming down 2 points from where it was, which puts it about there. All right, now let's take another look at a different kind of translation. This time we are going to be shifting it up or left and right horizontally. So again, let me get the parent function on there for us so we have it to look at. So it looks something like that. So for this one, we're going to start by shifting it left. So again, that's because it's the cube root of x minus a -1. That -1 is what's shifting it left 1. So every single point here is going to get shifted to the left 1, which means it's now shifted that way a little bit. The other way we can shift it horizontally is to shift it right. In this case, we are shifting it right 4 because it's minusing +4. So each point is now going to be shifted to the right 4 from the parent function. So that's going to go off our graph that way, but that's okay. This side will fit on our graph. So now shifted right 4 makes it like that. So you can see it's shifting that center point and then all the points from there. So we can shift it left or right by adding or subtracting that value inside the roots. Now let's look at our other two transformations that can go on. So in this case, we're going to start with dilations. So let's get that parent function on there just so we can see what those transformations look like compared to it. All right, so this time we are looking at dilation. So remember, that's multiplying by the a value out in front. If we multiply by an a value bigger than 1, in front, so any number bigger than 1, that's going to be a vertical stretch by that factor. So in this case, each value again is going to get multiplied by 2. So 0, 0 is not going to change again because 0 times anything is still 0. But this 0.11, if I multiply that by 2, it now comes up there. And if I multiply that point out by 2, it comes up here to 4. And then the same thing happens down below. So our curve is now stretched vertically, so it makes it a little taller in both directions, up and down. Opposite of that is a vertical compression. So let me get that parent function on there for us. So this one is going to be a compression because we're multiplying by when we multiply by a factor of 1/3, that's going to compress it closer to that x-axis. So each value is going to get closer by 1/3 to that x-axis. So it's going to be a very almost flat curve, but not quite. So it gets significantly closer to that x-axis in a compression. Okay, our last two transformations here are going to be reflections. So let's look at these. Get the parent function on there. Right, so the first one we're going to do is a reflection across the x-axis. So remember, when we reflect across the x-axis, all of the y values switch. So 0 is going to stay the same. That one doesn't change. But now when I reflect across the y, this right side of my graph is going to be going downward. Reflecting across the x changes those y's coordinates. And the left side of the graph is going to be up above our x-axis now. So it now looks like that. Reflecting across the y-axis, now we're multiplying the x values by a negative so that they flip. And what happens here is kind of interesting because if we look at our parent function, because this S-curve is shaped the way it is, when we reflect it across the y-axis now, the same thing happens that happened when we reflected across the x. So for these transformations, the only way to know if it's a reflection across the x or the y is to look at the equation and look at where the negative is. If it's outside the radical, then it is a reflection across the x-axis. If it's inside the radical, it's a reflection across the x-axis. Those are our transformations for radical functions. We'll see you next time.